All right, so this week we are going to be working through this chapter 6, data analysis t-tests and ANOVA. So these are two statistical tests that you use when you're trying to compare the average across multiple groups. So if you have two different groups of data that you want to say is one statistically significantly different than the other, if you've only got two groups, you're going to use a t-test. If you have more than two groups, you're going to use ANOVA. So before I go into these tests, I'm going to go over a few of the really basic principles for both as far as data assumptions that make it either appropriate or not appropriate to use these sorts of tests. And then if they don't meet some assumptions, what the alternatives might be when you're trying to still answer that question of, are these two means significantly different? So I'm going to do a bit of an experiment here. I'm going to open up, don't do what I just did, let's be better about it. I'm going to open up my R projects for this class. And I'm going to start a new R Markdown, and I'm going to call it t-test and ANOVA. Name it whatever you'd like. You also don't have to follow along, but if you would like to. Oop. Make that big for us. I'm going to get rid of. And because I'm doing this R Markdown in my R project, I've already got that setup script. This week we're actually going to be adding a handful of new packages to our setup script. I believe it's, let me look at the lesson plan here. So we've got the LTER data sampler package. I'm going to just keep appending new packages to the end there. And then another package called R statics. So this LTER data sampler is another data product package, much like our Palmer's Penguins, where it allows you to access a bunch of real data. And this data comes from the long-term ecological LTER. What's the R stand for? Research, yeah. Of course. But essentially across the country, there are locations that they've been collecting data for years and years, which allows for a lot of really cool research questions to be answered. And so this week, I think we're pulling data from a forest where they've had a handful of different sort of forest treatments, so clear cut versus old growth, and they're able to look at how species, I think they have a handful of different measurements across a handful of different species to see how differences may or may not be occurring within those different forest types. I think there's the salamander. We've got, they're all in the lesson plan. I can't remember off the top. Yeah, we've got trout, mostly vertebrates, I believe. But what we want to do this week is compare some of these different species and how there may or may not be differences across different forest types, etc. So I'm going to actually kind of not follow along with the lesson plan right now, and instead I'm going to just start writing a few things in my R Markdown that I find really helpful. Once you start going through a statistical test, there's a lot of decisions you have to make, and depending on what your data looks like, it kind of takes you down a different path one way or the other. So I'm going to just write all of those out. I usually do it on the whiteboard, but because I'm recording, I'm going to try to do this a little differently. So bear with me if this doesn't work. But essentially, I'm going to just write some notes at the top of my R Markdown. So there are a handful of data assumptions that come back over and over again with multiple tests. One of the big assumptions with both the t-test and the ANOVA is that you need to have a large enough sample size to be able to perform that test. So there's no really hard limit, but typically you want at least 20 to 30 observations, or rows in your data set, for every group you're trying to compare. So the reason behind this is actually, this may sound familiar to you, but the central limit theorem, which is that the more observations you have, the greater likelihood that your data is going to create a normal distribution. And so more on that later, but just know that you should tend to have at least 20 to 30. If you don't, there are ways of going about making it still appropriate, but at least for this class, you're never going to need to worry about not having enough data. But it's very important when you're doing your own research to try to make sure that you have enough observations to give yourself that strength in your statistical test. So the other one with a lot of statistical tests, especially and including the t-test and ANOVA, is that all of your samples need to be independent of each other. And what I mean by that is that there's no sort of relationship that's going on between observations within the group or even the two groups themselves. So the one that always comes to mind for me as a hydrologist, I'm always working with time series data. If you have anything that's time series, clearly there's going to be some sort of relationship between one observation to the other, right? Oftentimes the past dictates what's occurring in the present. So that sort of thing, not very useful to be doing something like a t-test or an ANOVA without doing a few things to the data set itself. So independent samples. And then another big one is having equal variance among the two or more, if you were doing ANOVA, categorical groups. So I've already said something about normal distribution and equal variance. I'm going to actually add here between my 20 to 30 observations and my independent samples that if you don't have enough samples, normal distribution must also be met. So what is a normal distribution and what is equal variance? So I'm going to go to the whiteboard because I don't know how I'm going to be able to write this without just showing you the difference. Can anyone even see that in the back? No? Okay, I'm going to make this really, really big. So this just says equal variance. So what equal variance is let's say we have two different groups of data that we're collecting an observation on. That observation is just X, let's call it. And then on the y-axis, we just have a count. So we're basically creating a histogram, right? So equal variance has to do with the shape or tightness. Oh, great. Thank you. They don't have any markers in this building. I went down to the office down there and they gave me these. Very good. Okay, I'm going to overwrite that here. Oh, that's much better.
Thank you.
Thank you so much. Okay. So, what equal variance means is that essentially the width of the histogram is the same across your groups. So if we have one of our group types whose distribution of whatever this X variable is nice and tight, a big peak, right? So this is basically the mean. And you have in your other distribution, or pardon me, in your other group, you have, it's a different group, so it might not be the exact same, but it looks something like this. We would not call that having equal variance. What that means is the variance from the mean is very different. Your standard deviation is very different from this distribution versus that one, right? We've got a nice tight distance away from the mean for the vast majority of our observations in this instance. Whereas here, we have a lot of data pretty far away from that mean. So this is an assumption that must be met for both the t-test and the ANOVA. What would be good is if they both looked like that, right? That's good. So that's equal variance. And then I'm going to go over here and talk about normal distribution. So normal distribution is, I think, for both the t-test and ANOVA, something that is assumed your data has. So once again, you kind of need to meet this assumption. When you have a huge amount of observations, so really anything over that 20, 30 mark we call fine, we can kind of assume, even if our data doesn't look like this, that it will get there eventually, based on the central limit theorem. But what a normal distribution is really just having a nice bell curve shape. So your bell curve can look like this. It could look like what we had there. That's still normally distributed, right? It's kind of like a mirror image from the mean on both sides. That's what we call normal distribution. There can be plenty of data sets that don't look like that. You can have right skewed, where you might have a long tail on one side. Is that right skew? That's left skew, actually. And then right skew would be the same thing. This is going to start looking really freaky. But just note that most data needs to look like this one. And so, if that's not met, there's a few ways of being able to statistically test that. Because just with your eyes, there's sometimes, you know, like, yep, that's normal distribution. But statistically, to make that test, there's a couple different ways to do it. Let's see. So for our normal distribution, the test that we use is the Shapiro-Wilks test. And then with our equal variance among the two categorical groups, so to test whether or not our two or more groups have that equal variance, so similar peakiness, the test that we perform for that is the Levene's test. Okay, so what happens if you find either your data isn't normally distributed, if you have a sample size below 30, or regardless of how big your sample size is, you don't have equal variance? There's two kind of approaches that you can take for your data sets. So the first one is that there are a lot of transformations that you can do across your entire data set to get their shape to look a little different. Some of the most common ones are log transforming. So you can do the log, which is the natural log. Log 10 is actually the base 10. And then there's to square root transform. Those I'd say are like the top three that I try to use. And oftentimes, depending on what your data looks like, one of these things will actually get the job done. So once you've transformed your data, you're going to want to still run these same tests to ensure that this new approach works. But once you've done that, you can just move along and actually follow that statistical test. So those are the two tests that we typically do before actually selecting and choosing which of the statistical tests we want to use to identify whether or not these two groups or more, if ANOVA is what you're doing, if they are significantly different. But once you know whether or not your data is meeting those assumptions or isn't meeting those assumptions, let's say even after transforming your data, it's still not meeting those assumptions, there's basically two different tests for both the t-test and the ANOVA. So for the t-test, if your assumptions are met, you can just perform the t-test function in R. Within that function, there's an argument that's, I believe, var.equal equals true. What we're saying is our data does in fact have equal variance, so we're able to perform the t-test as it should be performed. But if your assumptions are still not met, even after trying to transform your data, you have the option of doing what is called the Welsh t-test, but in R, using the rstatics package, it's still just that exact same function. You just want to make sure that you're setting your var equal to false. So with ANOVA, we also have like these two kind of sister functions that we can use if we do or do not have those data assumptions being met. For ANOVA, you use the ANOVA test function if they are being met. And then if they're not met, we use something called the Kruskal-Wallis test. And I think it's also written like that. So the only other thing I want to mention is when we talk about assumptions being met or not being met, we define the different statistical tests that go with each as being either parametric or non-parametric. So that's kind of synonymous with either meeting those equal variance normal distribution assumptions or not meeting them. So here I'm going to call, just to have it written out here, the parametric approach, and then the non-parametric approach. And I'm just writing this out because we use these words very often to call something parametric or non-parametric. Okay, and once again, all of this is also in that video that I shared. That's at the top of the book down. So with that, I suggest either watching that video if it's all sounding foreign. If not, just following along with chapter 6. So all of those tests that I laid out in the R Markdown are all written out here. Talk about the syntax required for each of these tests, what those tests are actually doing, and how you interpret the p-value. And if you have any questions, please don't hesitate to reach out here. This one, because we're introducing such a lot of new statistical concepts that may or may not be familiar to you, don't hesitate to reach out. You're probably not the only one feeling alone. So it might be that on Wednesday I'll go over some of the ones that are pain points for the rest of y'all, Yep. The video, so if you're in the book down and you are at the top of the data analysis t-tests in ANOVA, there's a link here at the top. We should probably...
I just added it to Canvas too in the videos module.
And then everything I just said, whether or not it's actually helpful, is also going to go on Canvas for y'all.